Hello, everyone. I'm Tanya. I'm one of the TAs assigned to the course Aircraft Design taught by Professor A.K. Ghosh. So we will be going over the assignments that you've submitted last week, and we'll discuss a few concepts that will help you solve the assignment of week 3. Okay, so all of you were able to solve the assignments. Have you all submitted the assignments? 1 and 2?
Yes.
Yes, ma'am.
Okay, good. So we'll just go over those questions today. These are the same formulas that you have seen last time, but I'm just going to keep this slide there to refresh your memory. So we keep using these formulas throughout the course. So first one is the coefficient of lift, which is the linearized equation with respect to angle of attack alpha. CD is the drag polar equation, which represents the induced and the parasitic drag. Thrust required, we derived this, there was a short derivation to get this expression. It's just a manipulation of the terms for level flight. From there, we get the equation for velocity at any particular given CL. And if it is for stalling velocity, then you have CL max. Then we had discussed this difference between the minimum thrust required condition and minimum power condition. There were a couple of questions in the assignment, in the forum, which is why I've introduced one more line here. So when they say just maximum range or maximum endurance, by default, it refers to the propeller case, right? This is the first row. But if they specifically mention that it's a jet engine, then it is maximum endurance for the minimum thrust required case and maximum range for the minimum power required case. Okay, so it's the opposite. This was a question that was asked, I think, twice in the forum. So I just thought I'll address this. It's the reverse jet engine. Okay, so it's the reverse for the jet engine. When they don't mention anything explicitly, you assume that it's the propeller case and take that minimum thrust required is maximum range and minimum power required is maximum endurance. Okay, so the other formulas are what we had discussed in the previous class. It's just the difference between the two cases. Now, why is this difference there between the propeller driven engine and the jet engine? What is the difference between their operations? Simplest way that you can explain.
Ma'am, in a jet engine, the turbines move inside the engine and pressurize the air to create the thrust. Whereas in propeller, the a propeller is present outside which sucks the air inside to create a pressurized air inside the jet engine to create the thrust.
Okay, correct. Yes, you're right. So what propeller does effectively is that it moves a large amount of air relatively slowly. In contrast, what a jet engine does is moves a small amount of air quickly. So what happens is that in the propeller case, you have an almost constant power output. Okay, but in the turbojet case or any jet engine case, you have a relatively constant thrust. So which is seen in this graphical representation here, that for a propeller case, the power that it generates, it produces remains relatively constant with velocity and decreases with altitude. Whereas in the turbojet case, the power increases with velocity, right? So the equation is the same, P equal to TV, but when each of those parameters is rendered constant, the variation with velocity can be observed. So whereas thrust is concerned for propeller, you have thrust reducing with the airspeed and reducing with altitude. Similarly, for the turbojet, you have thrust that remains relatively constant with airspeed. All of these quantities reduce with altitude. That is given. Okay. So this is why there is a difference in the operation, difference in the maximum endurance, maximum range of the jet engine and the propeller engine. So when these equations were derived initially, we did not have jet engines. It's with the invention of the jet engines that we realized that it's the opposite. So when they do not explicitly mention in the question that it is jet or propeller, you assume propeller and go ahead with your questions. So this, I just wanted to address this. Now, in the last week, one of the main topics that was discussed was the various considerations for designing an aircraft. One of them was the wing or the airfoil considerations. The different parameters that play a role while designing this wing are given here. First is CL alpha. CL alpha comes from this CL equation. CL is CL naught plus CL alpha into alpha, where CL alpha is just the slope, dCl upon d alpha of this graph, CL versus alpha, right? So we want this quantity to increase. Why? For a small change in angle of attack, you need large lift to be produced, right? So if there is a small change in angle of attack, a large lift produced is beneficial for us. So we need our CL alpha to increase. We need it to be a higher quantity because it's better. So for small change in alpha, you get a larger production in the lift. Next parameter that we have is alpha stall. Last class, we had discussed that alpha stall or stalling occurs when there is a flow separation over the airfoil surface. So if this is the angle, if it's flying at the alpha stall, there occurs a flow separation here such that it does not generate enough lift to balance the weight. So it will not fly, it will stall. So the angle of attack at which this phenomenon occurs is called alpha stall. So it is beneficial for us to delay this alpha stall as far as possible. So delay the flow separation as much as possible. That is, maybe have it here or maybe have it at a higher angle of attack. So that is another parameter that we need to take into consideration while choosing the airfoil wing cross section. What else contributes towards this flow separation? It's the CL max. That is also along the same lines, works along the same line. So you want your CL max to be as high as possible to increase the alpha stall. Okay, so to give you a larger operational range, you want your CL max, design CL max, to be as large as possible. Next quantity that we have is critical Mach number. What is critical Mach number? Can anyone tell me what is critical Mach number?
Ma'am, it is the value of the free stream Mach number at which flow becomes sonic for the first time over the aerofoil.
Yes, he's absolutely right. What he said is that it is the Mach number, it's the free stream Mach number for which at some point on the airfoil cross section, you have Mach 1 occurring at the first, this is the first point, right? So that is the critical Mach number. Again, you need the critical Mach number to be as high as possible to increase your operational range. So if suppose your critical Mach number is 0.7, so as soon as you reach 0.7, there is some point on the airfoil where you have shock waves, and then that is not beneficial for your flight. So you want this critical Mach number to be as high as possible so that you can fly for that duration without having any disruption in your, just a minute. Okay. So without having any disruption in your flight. So you need this also to be as high as possible. Next, another parameter here is CMAC. CMAC is from the stability aspect, stability control aspect. What is CMAC? CMAC of the wing. What is CMAC?
Moment coefficient of the aircraft.
Yes. So it is the pitching moment coefficient about the aerodynamic center of the wing. Okay. In this case, it's the wing. We're discussing wing. So CMAC is the pitching moment coefficient about the aerodynamic center. We require this to be positive. Why do we want it to be positive? So your stability equation, so pitching moment equation is Cm naught plus dCm upon d alpha into alpha. As far as stability is concerned, what do we need? We need this quantity to be positive or negative. This Cm alpha should be positive or negative for stability. For longitudinal stability.
Should be negative.
Should be negative, correct. So your graph should have a negative slope, your Cm versus alpha. Can anyone tell me why it should be negative from the physical aspect? We had discussed this in the last class. What is its physical significance? It should be negative, I agree. That is the right answer. Why should it be negative?
Then if we guess if a gust is coming upon from down, then the wing will be tilted up, but the inherent stability, the Cm alpha, will help him to come down it easily.
Yes, you're absolutely right. So just a few corrections in the terminology. It's nose up and nose down. Okay, pitch up, pitch down. You mentioned it's the entire aircraft. He's absolutely right. So you need it to produce a countering moment so that it returns to, or at least has a tendency to return to equilibrium. which is why you need your Cm alpha to be negative. That is, for a positive disturbance in alpha, you need a negative restoring moment. That's why your Cm alpha should be negative. Now here it says CMAC should be positive. CMAC of the wing is nothing but this value, that is Cm naught, right? Why is it desirable to have a positive Cm naught? Why can't I have a line like this? This also has a negative.
Because at zero lift angle of attack, the wing should be pitched up in order to maintain a positive lift. So inherently, if the airplane is in pitch down position, the zero angle of attack, then CMAC will help him to pitch up.
Exactly. So why we need the Cm naught to be positive is that, I'm just rephrasing your answer, is that we need to be able to trim the aircraft at a positive angle of attack. Okay, so we don't want it to trim. So this is the trim point if this were the graph. We don't want to trim the aircraft at a negative angle of attack. We want to trim it at positive angle of attack. So which is why we need Cm naught to be positive. It's desirable for it to be positive. It's not mandatory from the stability point of view, but we want it to be positive because of the reason that he mentioned. We want it to have trim at a positive angle of attack. Now these are the derivatives and the terminologies with respect to stability, control, and aerodynamic aspects. What are the properties of the airfoil that govern or that changes all these quantities? They are the nose radius, thickness to chord ratio, the mean camber line, all of those things, right? Few of those points, the nose radius and thickness to chord ratio. Anything else that you can think of? I have not mentioned all of them. The geometrical aspects of the airfoil that will help us to change these aerodynamic aspects. This is geometric. Any other quantities that you can think of?
Camber.
Camber, yes. What is camber?
The thickness, we can say that it is thickness, or we can say the mean camber line is up of the chord line, not along the chord line.
Yes, so I'll just draw an airfoil here. First, I'm drawing a symmetrical airfoil. So your chord line is here. And if I draw a midpoint from the top surface and bottom surface at every point, it lies exactly on the chord line, right? Which is how a symmetric airfoil is. Now, if I draw a positively cambered airfoil, if I have something like this, your chord line is here, but your camber line is here. So the camber here will be the maximum distance between the chord line and the mean camber line. Okay, he's right. What he said is right. It is the difference between the chord line and the camber line, the maximum distance. So any other geometrical parameter that will govern these quantities? Think about it. Maybe let me know next class. There are various geometrical aspects. You've studied the NACA series, so you know what are those quantities. Okay, so let's move on. So another question that was asked in the forum was, how is the velocity of the minimum pressure condition less than the velocity of the minimum drag condition? Okay, so this is the equation for velocity we had seen from the table here, right? From the set of equations. So this is the equation for velocity. Now I substituted the CL for minimum pressure and minimum drag conditions. So I substituted those CL values.
Shouldn't it be minimum power condition?
Sorry, yes, minimum power, my bad. Minimum power, thank you. Yeah, so this is minimum drag and this is minimum power. So I just substituted the values for the CL that we had seen from the table, and I've taken the square so that it's easier for us to compare. So these are the two expressions for minimum drag and minimum power. So the relation here shows us how they are related. The question in the forum was, how is the dynamic pressure of the minimum power case and minimum drag case different? What is dynamic pressure? Q is nothing but half rho V square. Now you can substitute the minimum power case and minimum drag case and see which is higher. I'm not sure who asked the question in the forum, but I hope this clears that doubt. Okay. So the only change here, if you keep everything else constant, if you keep density, that is altitude constant, if you keep the weight, wing area, everything constant, the only parameter that changes here is CL. And that is what changes the final velocity equation. So you only have a constant term here, √3, that signifies the relation between the two velocities. Okay. So yes, this was a question in the last class that I said we'll address later. So let me repeat the question again. For a jet-powered civilian aircraft, the thrust-to-weight ratio in climb flight will be. So these are the equations that we had derived last class, and we had seen that L/D is always greater than 1, and hence this term is always less than 1. And this term also, since the flight path angle is less than 90 degrees, the entire thing will be less than 1. So for a civilian aircraft, the flight path angle tends to be very, very small. Very, very small. Why? Why is it very small for a civilian aircraft? Why do we want it to be small? Flight path angle gamma.
Pardon, ma'am? What is the question?
Yeah. So I said that this gamma angle is very, very small for a civilian aircraft, flight path angle. Whereas for a fighter aircraft, it's almost always large values, right? It can have vertical takeoff. So why?
To allow comfortable flight for passengers,
Yes,
civilian
absolutely.
passengers.
Absolutely. So this value of gamma is very small for civilian aircraft, and hence this value is very minuscule. So for a civilian aircraft, this thrust to weight ratio is almost always less than 1. Okay. So from this relation, if you are to conclude that, it is by saying that this gamma is very small throughout the course of the flight. Whereas for a fighter aircraft or quadcopters or anything which has vertical takeoff, these assumptions will not remain valid. So this was a question from the last series. Moving on to assignment 1 questions. With increase in height, the density at the temperature. So we had studied the yes. Did someone say something? Okay. So in the previous class, we had seen that the standard atmospheric model. So when they ask such a question where it's not specified in which range, whether it's the troposphere or stratosphere, you assume the troposphere and move ahead with those assumptions. Okay, so here, when you see, this is the same image from the last time. So when the altitude increases, it goes from 0 to 10, what happens to pressure and temperature and density?
They decrease, ma'am.
Yes. What about temperature? Temperature also reduces here. So the rate of change of temperature here is called lapse rate, represented by gamma. Lapse rate. Right? So in the troposphere region, that is from 0 to about 11 kilometers, this value is negative. Then from this 11 to 20 kilometers, it remains constant. The temperature in that region remains constant. After that, the lapse rate is positive, so on and so forth. Okay, so when they ask a question without specifying the region, you assume troposphere. So in this case, density and temperature both reduce. Next question, which airfoil is preferably used for design of horizontal and vertical tail? We just discussed symmetric. Why? Symmetric is the right answer. Yes. Why?
Because we don't want any unwanted forces in any direction.
Exactly. So the main purpose of the horizontal and vertical tail is to contribute towards stability and to have some control surfaces on them to control the aircraft. We do not, its main purpose is not to produce lift in any direction, upward or downward. So it's preferably a symmetrical cross-section because we don't want any, like he said, unbalanced forces. So when you are deflecting, when you want it to produce different forces like lift upwards or downwards, that is when you deflect the control surfaces. So suppose you have your horizontal tail like this. Okay, it's not symmetric. So if you have your horizontal tail like this, and say you want it to produce a moment in this direction. So you need it to produce a force upwards. What do you do then? Then you deflect your control surface down. So this introduces some sort of a camber, right? There is an effective camber here, which produces a lift, which in turn produces the moment that you want. So for the horizontal and vertical tail to produce lift, we have control surfaces. We do not otherwise require it to produce any lift in the upward or downward direction, which is why almost always it's preferred to have symmetrical airfoil for horizontal and vertical tail, as its main purpose is not lift generation, it is stability and or control. Okay. Wing loading will affect what? Only stall speed, only climb rate, or both of them?
Both of them, ma'am.
Yes,
Both.
we know it. Yes, yes. So I'll just go over the equations. This is the same equation that we've seen from the first slide. So it directly depends on wing loading here. So V stall is obviously affected by wing loading. Rate of climb equation is this: T V infinity minus D in V infinity by W. So here, when you substitute the value of drag, that is when the W by S term comes into play. So when you substitute all of these quantities back into the rate of climb equation, you can see that W by S is present here. So obviously, the wing loading affects both the stalling velocity and the rate of climb. Okay. So next question is, the wing loading for an aircraft is 50 kg per meter square and maximum CL, that CL max is 2.4. Find the V stall. Fairly simple question. It's the same formula as the previous slide. This formula, substitute the values and we'll see what answer we get. Right, it's the same formula. So 2 W by S is directly given as 50. We have a 9.81. Density is 1.225. CL max is given as 2.4. What is this value? Just tell me the value quickly.
18 point some
18.2. 80%. Okay. So the next question is, find CL by CD max if drag polar of the aircraft is given by. So for CL by CD max, we had seen in the initial slide, what is the value of CD? What is the, is given, find CL by CD max, okay? So this part is the CD naught, and this is K, and this is the parasitic drag, and this is the induced drag, okay? This was again asked in the forum. Okay. So find CL by CD max. How do you do that? You find the value of CL. What was CL for this CL by CD max case? What was CL value? For the case where CL by CD is max, that is that minimum drag or minimum thrust required. What was the value of CL?
under root CD naught by K.
Under root CD naught by K. For the minimum power, what was the CL?
Under root 3 CD naught by K.
Very good, correct. So this is minimum drag, this is minimum power. So if I substitute the values, it is 0.05, by K is 0.08. What is this value? 7.9, right?
Yes, ma'am.
And these are just the equations that we just used. Okay. An aircraft wing has a positive cambered airfoil E124 from the Epler series. Which of the following graph correctly represents the graph between CL and alpha? Now, in the previous class, somebody had asked me that they weren't finding information on the Epler series.
Yes, ma'am. It was me, ma'am.
So, yeah, so Epler series is just a method of, what do we say? Like
Yes, on naming the aerofoils. Just,
naming the airfoils,
I
something
simply
similar to,
yes, ma'am. I simply read the question and found a positive camber. So that's I guess the correct answer.
yes, yes, so positive camber. So which is the correct answer here?
A.
A.
A, yes, A is the correct answer. Can you tell me why? How did you find out that it's a positive camber? What is the characteristic typical of a positive camber?
The characteristic of a camber aerofoil is that it produces more lift at zero alpha equal to 0. It
Yes,
lifts,
yes.
it lifts.
Absolutely. What about the second case? What is this? What does this show?
Symmetrical.
Symmetric. So this is positive camber. This is symmetric. This is
Negative cambered, ma'am.
negative camber. And what about this? It produces no lift at any, it produces constant lift at all angles of attack. I'm not sure where we use that or where.
Ma'am, This type
such
of
thing
wing
doesn't
is
exist,
not
ma'am.
aerofoil, exist, no, ma'am.
It doesn't exist, exactly. Even if you have a flat plate, it will produce lift at some amount of lift at different angles of attack. You're right. Okay, so what about negative camber? Where do we use negative camber? Anyone has any idea? Why do we use negative camber?
Maybe sometimes at tail surfaces for horizontal stability.
Okay. So you guys look this up and let me know in the next class where this negative camber airfoils are used. They are used. Just tell me in the next class, okay? With positive camber in the airfoil, alpha stall increases, decreases, remains unchanged, cannot say,
Decreases.
decreases. Anybody else has any other answer? Can you tell me why it decreases?
Because my flow separation will occur
At
prematurely.
lower angle.
Yes, yes. Okay, so that is correct. So if I would, the graph, right? So if you have a positive camber keeping all of the characteristics same, you just shift the graph slightly here. So that was right. So all other properties remain same. You just move the graph here. So all of those alpha at properties that are associated with the alpha are shifted towards the negative side of the x-axis. X-axis in this case is alpha. So all those characters, suppose this was your alpha stall, it has moved to this side now. Okay, it has moved, it has reduced, which is why with a positive camber, the alpha stall reduces. It stalls at an earlier angle. Like he said, flow separation occurs prematurely. Okay. Which of the following statements are true for a typical flight profile of quadrotor UAV and fixed wing UAV? So what is the difference between these two cases? Main difference.
A quadrotor doesn't have a wing.
Okay. Okay. So how does it produce its
It
forces?
produces lift purely from thrust.
Okay, yes. So it only has, so if it has 4 rotors, it produces thrust in the upward direction. And this completely balances your weight. If it has to remain at a particular altitude, if it has to hover, thrust is the only thing that balances your weight. Okay. So for it to lift, for it to climb, the thrust has to be greater than weight. So the first one for quad rotor, thrust by W has to be greater than 1. T by W for quad rotor has to be greater than 1. What about for a fixed wing case? Fixed wing case is similar to a regular aircraft, right? So
Yes.
that will not be greater than 1. We just discussed in the previous question that will be less than 1. So the correct answer here is this. Now, for quad rotor, if your only force generated is thrust, it can take off. If the thrust is greater than the weight, it will take off. If you needed to remain at a particular altitude, you equal the weight with the thrust. How will it move forward?
By increasing the thrust of back to rotor.
Okay, and how will it roll?
Increasing the thrust of, like if we want to roll to right, then we increase the thrust of to left rotor.
Okay. And what about yaw control? Yaw, how do we control?
It is controlled by making the speeds of the diagonal rotors change slightly.
Slightly, correct. Absolutely right. So this is a very interesting case where we only have one force. We only have thrust. We don't have any other lift generation mechanism. And yet we're able to control all the 3 attitudes. Okay. Why do we have, if you can control all 3 attitudes with just thrust and you also have vertical takeoff landing, why do we also have fixed wing UAVs?
Because they consume very less power or fuel, which is economical.
Okay.
And ma'am, also the thing is that
You're muted. Achyut, you're muted.
For
Yes.
quadrotor, ma'am, the aerodynamics will be not as favorable as the fixed wing UAV, because fixed wing UAV is designed for cruising, ma'am. So
Yes.
if it cruises, it will consume less power, and with the help of aerodynamics, it can move much faster and much easily as compared to quadrotor.
Yes. Yes. Both of you are right. So then why do we have quadrotor? Is it only for the vertical takeoff and landing?
Ma'am, it is good for the places where we cannot have a large landing space. It is used, it will be helpful for rescue missions or the hilly areas where vertical takeoff and landing will be much easier than landing and taking off.
Okay. Okay. Yes. Absolutely right. Both of you have given great answers. Absolutely right. Okay. So let's move on to the next question. The primary control for angle of attack is? What is the primary control?
Elevator, ma'am.
Elevator.
Okay. So this question, like the question that we discussed last class we had something that asked what is the primary control for side slip? What was the primary control for side slip?
Rudder.
Rudder. Okay, so when we discussed that, I had told that our attitude angles are phi, theta, and psi. Phi being roll, theta being pitch, and psi being yaw. So these are the values that we can control. Okay. So the other angles that are alpha and side slip, that is angle of attack and side slip, are what happens by virtue of how the velocity hits your aircraft. Okay. So if it's from the side view and this is your fuselage reference line, this is the oncoming velocity V infinity. And this is your chord line. So this is the angle of attack. You cannot control the angle of attack. You can control only your pitch. Similarly, from the top view, if this is your fuselage reference line, this was your initial V infinity, and now due to gust, you have another V infinity has changed. This is your side slip. You can change only the yaw. Okay, you cannot control side slip or angle of attack. So this question is slightly problematic, in which it says you can control angle of attack. You cannot control angle of attack because that is determined by the V infinity, by the free stream velocity. So what it should have been is primary control for pitch. But yes, the axis about which it controls is the same. That's longitudinal control, and the answer is elevator. We'll just look at it. So if you deflect your elevator up, right, it produces a camber in this direction. Hence, the force will be produced here. So you have a moment like this. So it produces a nose up. So if you were to pitch your, if you were to deflect your elevator down, deflect it down, you have a camber that's produced like this, and your lift will be produced upwards, which produces a nose down moment about the CG. Okay, this is how the elevator works, similar to the other axis. This is for the longitudinal axis. So you must remember that the angles that you can control are phi, theta, psi, roll, pitch, and yaw. The angles that are by virtue of how your free stream velocity is, they are alpha and beta, and we cannot control them. We can effectively change them, but we are not, the definition, by definition, it is defined by the free stream velocity. You can't change the direction of free stream velocity. What we can change is the orientation of our aircraft, which is defined by phi, theta, and psi. Okay. So next question. Which one is correct about the static margin at neutral point of an aircraft? What is static margin?
It is the point at which the CG and the neutral point of the aircraft almost meets together, ma'am.
Okay, static margin is, like the name suggests, it's a margin, right? So it's a length, right?
Difference
Yes,
between
ma'am.
position of neutral point and center of gravity.
Correct, correct. So for a stable, inherently stable aircraft, the value of static margin should be what? Positive or negative? Okay. So your static margin equation is, it's basically the negative of the slope between CM and CL. So he is right. He said it's a difference between the neutral point and CG. So if this is your fuselage reference line, and if this is your neutral point, where should the CG for a stable aircraft be?
Head of neutral point.
Ahead, yes. So
Ma'am,
if you,
can you
yes.
please increase the brightness of the screen sharing, ma'am?
It's at maximum brightness. Can you see now?
Yeah, yes, ma'am.
Maybe I'll increase. Can you see? Is it clear?
Yes, ma'am.
So yeah, for a stable aircraft, the CG has to be ahead of the neutral point. So what will be the static margin for a stable aircraft? If your reference point is somewhere here, and this
Between
is
neutral
your,
point and
yes. Can you hear me?
yes, ma'am.
Yeah, okay. So for a stable aircraft, static margin value should be what?
Greater than 0.
0.
Yes, okay. So the question here is, which one is correct about the static margin if your CG is at neutral point? So value, if your CG and neutral point are the same, what will static margin be?
Equal to 0.
Exactly, exactly. So it's
Equal to 0.
exactly correct, correct. It is 0. Okay, now we move on to questions of assignment 2. An aircraft is equipped with a symmetrical airfoil. For complete aircraft, the lift curve slope is given by 0.09 degrees. Maximum alpha, that's a stall angle. It's maximum angle at which we can fly. It's 15 degrees. What is the stall velocity if the wing area is given, wing loading is given, and density and other regular parameters are given? So again, it's a simple formula for stall velocity. It's the same formula. Let's just go ahead with it. So it's 2 and wing loading is 41. G is 9.81. Density is 1.225. What is CL max? What is CL max?
Ma'am, under root of CD naught by K.
Airfoil is given to you, right? So this is your profile for the airfoil. And they've given you the maximum alpha. That is the stalling alpha. They've given you this alpha. They've given you alpha stall. Now CL max is this point, right? This is CL max. How do you find out that point? They've given you the slope. You're assuming linear in nature. So our CL equation was CL naught, CL alpha into alpha. So in this case, CL naught is 0, right? So if you take alpha, CL max will be, in this case, CL naught is 0 plus CL alpha into alpha stall, right? So CL alpha here is 0.09 and maximum, that's alpha stall, is 15 degrees. So I substitute this here. We get 0.09 into 15. What is this value? V stall? 22.
Ma'am, 1.35, ma'am.
You're telling me CL max, right?
Yes, ma'am.
Yes.
Yes. So what about this value?
22.05.
22.05.
Yes. Meters per second. So that is the correct answer. Next is, so they're giving you data for the next few questions. An aircraft has a wing area of 23.69 meters square. Weight is given. They've given you drag polar and the other parameters. So L by D max is what they've asked you to calculate. We just did a similar question now. So for the L by D maximum case, what is CL? What is CL?
Ma'am, under root of 3 CD naught by K.
For L by D maximum case, when will this L by D be maximum? When drag is minimum. So for minimum drag, what was the CL? We just did this question. if your drag has to be minimum drag condition, what is the CL? CD naught by K, right?
Yes, ma'am.
So it is 0.023 by 0.0735. Okay, so now they've asked you for the ratio, which is just CL upon CD, which will be, what is this value? Just calculate and let me know what is the value. What is the value? 0.023 divided by 0.0735. Square root of that is 0.55. 0.55 by CD is 0.023 plus 0.0735 into 0.55, which is, what is the final answer? Just calculate this value and tell me what is the final answer.
Ma'am, as per the key, it is showing
12.16.
12.16.
12.16.
So even with calculation, it is 12, right?
No, ma'am. It's showing 2.033, ma'am.
Are you sure? Can anybody else verify?
Ma'am, it's 12.16.
But let me just do calculation.
Ma'am, I'm getting 12.16.
Yes. Yeah, I'm also getting 12.1. Who was different answer? Can you just do the calculation again?
I got the different answer, ma'am. Once again, I'm checking, ma'am.
Yeah, please do that.
Ma'am, I got 8.69, ma'am.
Let me just check, okay? I don't really have a calculator. Is everyone? I'm getting 12.16.
Yes, ma'am, it is 12.16, even by the
Okay.
formula.
Yes. So it's 12.16. Please check your answers again. The different answers. It is 12.16. Let's just try it a different way. So your CL was CD naught by K is C naught plus K CL square, which will be CD naught by K, which is 2 CD naught. So CL is 2 CD naught. Right, so you're getting this value as 0.55. This value will be how much? 0.046. CL by CD. Just divide these two. Yeah, it's coming around 12 only. Okay, just verify your answers again. Whoever.
Yes, ma'am, 12.
Yes. Yeah. So I'm just going ahead. Something in the chat box. Badavat, I'm sorry if I'm pronouncing it wrong, but are you getting 12.6, 12.1? Okay, so I think almost all of us are getting 12.16. Please check your answers again. And if it's still some error there, please put it up on the forum. Okay, we'll just move ahead now. Okay. So for the same aircraft, this is the same equation. We used these equations and got the answer. The CL at minimum drag. Okay, so we just calculated this. CL at minimum drag was nothing but CD naught upon K, which was 0.55. Okay, so it comes to about this. It's approximately that. Equation there. Okay. Calculate velocity at minimum drag. So we have CL, we can calculate velocity. What was the equation for velocity? That was 2W upon S by rho CL. So that is 2W upon S was what? What was the value? So weight was 4535.93. Okay.
Ma'am, answer is option B, ma'am, 74.04.
Okay. Last class, somebody had mentioned that they were getting the squared values of velocity. I'm not sure who asked that question, but
Yes, ma'am, it was me.
are you getting the right answer now?
Yes, ma'am. Now got it, ma'am.
Okay. Okay. 4535.35 into 9.81 by 1.225, and CL was around 0.55. There's also an S here, so that's what's 23.9 square root. It comes to 74.04 meter per second. Okay, so second option, he's right. That is the right answer. So this is the equation that we used. Now, what is the value of minimum drag? So what is the equation for drag or any aerodynamic force for that matter is half rho v square S CD. So CD we just calculated. We just in the previous question, that is question number 4. S is given, rho is given. So let's do that. Into 1.225. V was 74 point something square. S was 23.69. CD was how much?
0.023.
Okay. So the final answer was, what does it come to?
3,659.09 newtons.
Perfect. So that is available, option number 2. Okay, so yeah, this is the equation that we used. Now this question, it gives the plot between the power required and velocity. So the first question is straightforward. What does point A represent? It is the, what is it? It's the minimum point on the curve. So it is the minimum power required. Very simple question, right? So it is minimum power required. Next is, what does point B represent on the curve? Point B.
Maximum, ma'am.
What does it represent?
Maximum power required.
You
I
sure?
got it wrong on the assignment, ma'am. No, it is fourth option, CL by CD max.
It is CL by CD max. Why did you say maximum power required? Can you tell me? So if we have any graph, right? So if you have any graph that goes anyhow, because it goes like this, there's no discontinuity. So if you have any graph like this, what is the minimum point of this graph? It's here, right?
Yes, ma'am.
The maximum point is here. And if there were no maxima, if it's a graph like the one given in our figure, with something like this, the maximum point would just be the extreme point, right? That cannot be the maximum power required. What will it be? So it cannot, point B cannot be, not B. So Is it stall velocity? He told the right answer. The right answer as per the key is CL by CD max for point B. But why is it CL by CD max? What is CL by CD max? What is that case? So this minimum power required, we know. What was the other case? When is CL by CD maximum?
When power is minimum for propeller.
CL by CD is maximum. Okay, let's just see this. CL by CD, this quantity is maximum when your drag is minimum, right?
Yes, ma'am.
So CL by CD max corresponds to drag, minimum drag, which also means minimum thrust required. So here, this is in fact given in the question. What is the thrust required here? Thrust required is, we assume it to be drag for the level flight condition. From this graph, what will it be? It will just be power required by velocity, right? So this represents a constant slope line. Correct? So TR equals PR by V. If you take it to be an equation of a straight line, it's a constant slope line. Correct?
Yes, ma'am. Minimum slope.
Okay. And we require this thrust required to be minimum. So basically you take the slope, you take multiple lines, you take any constant slope lines along this graph, and whichever line gives you the minimum slope, that is your minimum power required line, minimum thrust required line. So in this case, this is your minimum. So if you have, this angle is the least, right? If you make it any lesser, it will not intersect your graph at any point. So you cannot have this PR by V. So this is the minimum possible theta at which it will intersect the, not intersect the graph, it will touch the graph. Even intersect, even if you take intersect, this theta minimum, this dotted line is the minimum possible theta at which the line will intersect the graph at any point, intersect or touch the graph at any point. So this line represents the minimum thrust required, which in our case is the minimum, in this level flight condition, it's the minimum drag, and that represents CL by CD maximum, right? Is it convincing? Are you convinced?
Yes, ma'am.
Yes. Okay. So the constant slope line with the minimum slope gives you the minimum thrust required. So that is this point B. It represents the minimum drag condition or minimum thrust required condition, which is nothing but CL by CD maximum. So point B is CL by CD maximum. Point A was minimum power required. It was simple. Okay. Yeah. So this is how we arrived at that. So this is the various constant slope lines, that power required by V. This is the power required by V. So the least value at which it intersects the graph will give you L by D maximum. Okay. Now, an aircraft has a gross weight of 2,700 kgs. At the end of the mission segment, it has a weight fraction as 0.85. Determine the fuel consumed during this mission. How would we do this? I had given a hint in the previous session. So weight required at the beginning of the, the weight fraction at the beginning of the flight is nothing but weight initial by weight initial, which is 1. Now after the mission, it is weight final by weight initial, which is given as 0.85. Correct?
Yes, ma'am.
So what changed between these two weights? It's just the fuel consumed. So if I were to just subtract it, so it's weight required minus weight final by weight initial gives you weight of the fuel consumed by initial weight. Now this is nothing but 1 minus 0.85. So weight of fuel consumed is W naught, that is the initial weight of the aircraft, into this. That is 2700 into 1 minus 0.85. How much will that come to?
405 kg.
405. Okay, so that is the right answer. So the difference between these two ratios gives us an indication of how much fuel was consumed in the entire mission. So using these values, you can try to estimate how much fuel you should be carrying on board for if your mission is specified. That's how you design the weight. Along the similar lines is this question that you have an initial. So you have W naught here with a fuel fraction of 0.28. Then what will be the weight of the fuel in kg? It's very simple. So weight of fuel by weight initial is given as 0.28. So weight of fuel will be 0.28 into W naught, which is 0.28 into 5100. And how much is this value?
Ma'am, 1428.
Absolutely. Yes. So I hope all of you got all of these questions right, or at least it's clarified now after the session. Is there any doubt in this in the first two assignments?
No, ma'am.
Okay.
Ma'am,
Let's
but
move on.
please
Yes.
show me the static margin equation, ma'am.
Yes, just a minute. So this was the equation for static margin. It's the difference between the lengths of the neutral point. It's a distance between the neutral point and the center of gravity. Yes?
Yes, ma'am. Ma'am, and also the difference of maximum endurance and minimum endurance, as you showed in the beginning of the session, ma'am.
You want me to explain it again?
No, ma'am, I just want it so that I can note it down, ma'am.
Okay, yeah, sure. I'll just show you that table. Yeah, so for a propeller case, it is the maximum range is corresponding to the minimum thrust required condition. And similarly, maximum endurance corresponds to the minimum power required. It's the exact opposite for jet engines. Okay. Have you noted it down?
No, ma'am, I'm noting it down, ma'am.
Okay, yeah. You can take a screenshot or these slides will be shared with you.
Okay,
so
ma'am.
I'll go ahead. So if there are no further questions, then we'll just go to the few other questions that will help you solve the week 3 assignment. So this is the data that is given to you for a few questions that will follow. The total weight of a fixed wing aircraft is given by, so VTO is weight at takeoff. So the sum of all the weights of all the components, that's the avionics, subsystems, propellant, the fuel, it's the power plant, other weight, structural weight, payload weight, all of them. So it's the sum of all of them gives you the takeoff weight. Right, so it's given here structural weight, subsystem weight, propulsion system weight, that's the power plant, the engine, the avionics weight, all the other erroneous weights, the payload weights, the fuel weight, okay? And they've given you the various mass fractions. So the fixed wing propeller powered aircraft has the following characteristics. Mass fraction of the structure is given as 0.23. What is the mass fraction? It is the weight of the structure by the overall takeoff weight. Similarly, for the subsystem, it is given as 0.05. Then they've given you a ratio between the power and the weight, that ratio. Then they've given you BSFC, right? They've given you the mass fraction of the propeller, the propulsive system. The L by D max, they've given you CL trim, they've given you cruise airspeed, They've given you propeller efficiency, maximum range, wing area, and they've given you the sum of the components. So they've given you avionics, payloads, and other. That is given as 60 kgs. Now let's look at the questions. What is the value of the fuel mass fraction? I'll just give you some time to go through the question again and try to come up with an idea of how we will solve this. So they've given you a lot of data. Just go through it and see how we can solve this. How can we solve this? So I'll give you a hint. It's from some of the concepts in week 2, that is the range and the endurance. Can you try to get some clue from it? Where do we begin? So we begin, I'm just giving a hint, we begin with the range formula. So what was the range formula, maximum range? This is from week 2 contents. What was the range formula that was derived? The Breguet's range formula. For, in this case, for a propeller powered aircraft, what was the equation? Did you all go through week 2 lectures?
Yes.
Yes, ma'am.
Okay, so I'll just write down the range formula, okay? So range was, that is the efficiency of the propeller, which is given here. This is for a propeller case, okay? So specific fuel consumption. And it was CL upon CD. So I'm just writing L by D. Maximum, L by D max. And the logarithm of initial upon final. Yes? Do you remember this equation?
Yes, ma'am. Yes.
Okay. So now they've given you this range. We'll just substitute the values one by one. What was the range? Range was 1000. They've given you propeller efficiency as 0.65. What is SFC? SFC here is given.
Specific fuel consumption.
Specific fuel consumption.
Yes. So for this equation to be valid, what unit do we need SFC to be in? So SFC, I think in the it was represented by C in the lectures. We'll go ahead with that. It should be what? Newton per watt second, if I'm not wrong. This is it, right?
Yes, ma'am.
Watt second. So what is given to you is kg per kilowatt hour. So let's just convert it. So it will be 0.6 into 9.81, and it's given in kilowatts. So you have 1000. It's given in per hour. So you have to convert it to seconds. You have 3600. So what is this value? Or we'll just put it there as such. I think we'll just put it there as such. Or we'll calculate it. Can you just tell me this value? Let me try calculating it. Six into 9.81 divided by 1000.
1.63 into 10 is power minus 6.
1.63 10 raised to power minus 6 Newton per watt second. Yes, okay. So I'm just putting that value here. 1.63 into 10 raised to minus 6. The L by D ratio is given here. So I'm just putting it as such. CL by CD, L by D, same thing. And then you have logarithmic weight initial by weight final. So if you solve this, you get logarithmic of weight initial upon weight final to be. To solve this, What is the value? I'm guessing
Ma'am,
it's
it is coming out 0.000228. Very small.
okay. Okay, 1 minute. Okay, I think we've made a mistake somewhere. It should be 0.2. There is a where have we made the mistake? It should come somewhere around 0.2. If it's that small, it will not work. Where have we made the mistake? There is a 10 raised to power minus 3 error. Where have we made the mistake? Oh yes, oh yes. Kilometers. This should be in meters, right?
Yes, ma'am.
So range is given in kilometers. So you have 10 raised to power 3 here.
Yes, ma'am. Now 0.2279 or 0.228.
Okay. So 0.22 228, right?
Yes, ma'am.
Okay. So then if I take weight initial by weight final, if I take e power 0.228, what will it come to?
1.256.
1.256. Okay. So now what they've asked you the value of the fuel mass fraction. This is weight initial upon weight final. So our usual terms that we did in the previous question was the inverse of this. So let's just take that. Weight fuel upon weight initial is equal to 1 by 1.256. Right? Any questions so far? So the final weight is nothing but initial weight minus weight of the fuel consumed. Right? And then I retain the same equation 1 by 1.256. So this is 1 minus weight of fuel by weight initial, which is 1 by 1.256. So we get weight of fuel by weight initial or weight takeoff. This initial weight is nothing but takeoff weight. So VI is nothing but V takeoff. That gives you 1 minus 1 by 1.256. How much is this value?
Approximately 0.2.
Okay, so you have that option here. So is this clear? The procedure that we followed, they've given you the maximum range. You know the maximum range equation. This is the Breguet's formula. From that equation, we know propeller efficiency, we know SFC, specific fuel consumption in case of propellant system should be in these units. So we converted our kg per kilowatt hour into Newton per watt second. We plugged it into this equation. CL by CD max is given to you as 11. You put that here and then you found out this ratio. Please keep in mind the units. We did make a mistake while solving this now. So you need to keep in mind the units. The range is given in kilometers. So we had to convert it to meter, which was the step that we omitted. Okay, so make sure that you get your units right. So you got this ratio from which we just flipped it to get V final by V initial. I just did that to make it more convenient for getting the answer, but you can follow, once you get this ratio, you can follow any way to find out the weight of the fuel. What do you need to make sure that the final weight is nothing but initial weight minus weight of the fuel. Okay, so then you can perform some manipulations to find out the ratio between weight of fuel and V initial or W initial. So you follow these steps and you get a value of 0.2. So is this procedure clear? Right? You
Yes,
begin with this, you found out this ratio, and then you found out this ratio. So step 3 was here, and so you got your final answer here. So this process, I hope it's clear. Okay. Next question is, what is the weight of the aircraft? Here, it means what will be the takeoff weight? V initial or W takeoff. What will it be? That is the question. How will we go about doing this? They've given you the first equation. That is your hint. So it's not Okay, so you have W avionics. Then you have W subsystem. Then you have W of the power plant. Okay. Then you have all other miscellaneous weights. Then W of structure. Then W of payload. And W of fuel. Now, what are the weights that are directly given to you in this equation? You need to find out this. What are the other weights that are directly given to you in this question?
Avionics, payload, and other. These are all are given. 60
You
kg.
have avionics, payload, and other. So that is given to you. So that you put it as 60. Then you have weight of the subsystem, weight of the propeller, weight of structure, plus weight of the fuel. Now what I do, I just take this entire term on this side. So you have takeoff weight minus this entire term. So that is subsystem, propeller, structure, fuel equal to 60. Now for all of these terms, we have their ratios with respect to takeoff weight. So what I do, I take out the WTO common. So what do you get? 1 minus subsystem upon W takeoff minus propeller upon W takeoff minus W structure upon W takeoff minus weight of the fuel upon W takeoff equal to 60. So all of these terms we have. So 1 minus what is W subsystem by W takeoff? The value?
0.5 times the mass of subsystem.
0.05. Yes. Then propeller
0.23.
yes. Structure is 0.23. And this weight of fuel by takeoff weight we just found out in the previous question. What was the
0.2.
sorry?
0.2.
Yes.
0.2.
Yes. Is equal to 60. Okay. So now we just find out W takeoff as 60 upon this entire term. What is the value? The entire term. What is the value? Just calculate.
142.86.
Are you sure? I'm okay. Just try calculating it again. I'm getting something around 139 or something. I'm getting around 136.
Yes, ma'am. 136 point.
So it's around 137. Okay, I'm just going to take it as 137. Where that is the final answer. So is this clear? This sequence that we followed?
Clear now.
Clear. Okay. Now the next question is, what is the weight of the power plant in kg? Here we took W takeoff. Next question is, what is weight of the power plant? Power plant in our case is the propeller. So what is this? How do we go about doing this? If the previous question was clear, then this should be very simple. Someone tell me, how do we find out the weight of the power plant?
Ma'am, just multiply the weight, which is 137, by the weight fraction of propulsion.
Exactly, exactly. So you have that ratio, that is weight of the propeller by takeoff, which is given as 0.8. So you have prop to be 0.08 into 137, which is, what is the value? What is the value?
Approximately 11
10.96.
kg.
Yes.
10.96 kg. Okay. So that is the value. So similarly, you can find out the weight of any of these terms, that is structure, subsystem, weight of the fuel. In fact, you can do that as well. So what next question is, what is the peak power required in HP? They've given you the ratio between power and the weight. So P by W is given to you. P by W. Right? Now you have this W, you have this takeoff weight is given to you. They've asked you for peak power. What will be the maximum? If this ratio is given to you as 0.14, what will be the maximum power? Maximum power will correspond to the maximum weight, right? Yes, it's a simple multiplication. So obviously it will correspond to the maximum weight. Maximum weight in our case is the overall weight, the takeoff weight. So it's nothing but 0.14 into 137. What is this value? Why do we get maximum power initially? So maximum, this is peak power is given at takeoff. So why do we get this maximum power initially, not towards the end?
Ma'am, this is because while taking off, the weight of the aircraft will be more, ma'am, and it requires the maximum power to get it lift from the ground, ma'am.
Okay, yeah. So you have a lot of fuel at your disposal to use it to achieve the maximum power. So what is this value? Around
19.18.
19.
19. So 19 HP.
0.18.
Okay, yeah. So approximately 19. Okay. What will be the value of trim speed? So again, is very simple. How do you find out this?
Simple formula, ma'am. Under root 2 W by S upon rho CL trim. That is
CL
it.
trim. Exactly. So just substitute the values. It's 2 into 137.81 by rho is 1.225. S is 6 and CL trim is 0.3. So what is this value? Around 35?
34.9. Yes, 35.
Around 35 meters per second. So this is how we calculate this series of questions. With this, we finished that question. Now let's go to a next question, which is kind of interesting. So for a certain angle of attack at a given altitude, the lift will be doubled for which combinations of S and V? So we'll take out each combination and see. Okay. So what is the lift equation?
Half rho V square C CLS SCS.
Okay. So in this question, we are only varying S and C. So let's just keep those two as variables. The others will take as constants. So that will be half rho CL V square S. Okay. So this entire thing I'll take as some constant, some A V square S. Okay. So we'll try out this for each case. This A will be constant for this question, only for this question, because we are only varying V and S. So case 1. So lift 1 would be, so A, V is root 2V. So you have root 2 square V square and S is remaining S. So what do you get? You get 2A V square S. So the question was, in what case will the lift be doubled? In this case, is the lift doubled?
Yes, ma'am.
Yes.
In last case, yes.
So this is doubled. Next one. In this case,
Ma'am,
what do we
except
do?
for B, it won't be. Except for B, all it will be doubled.
Correct. So let's just write it down. So this will be 1 by 4 V square into 2S, which is A V square S by 2. Is not doubled, so not this one. So L3 will be A V square 2S. So this is doubled. And L4 will be A into 4V square by into S by 2, which is again doubled to AV square S. So this is also true. Okay. So this completes this question. I've just written down the equation that we used. Then the drag polar of an aircraft is given by the same drag polar equation. They've also given you a lift curve slope. What is the value of the parasitic drag coefficient? This is CD naught plus KCL square. So what is the parasitic drag here?
0.02 or
Yes.
CD naught.
CD naught is 0.02. And what is the coefficient of lift when it's operating at max CL lift by drag? We've done this question a lot of times. What is the CL at L by D max?
Twice of it, that is 0.04.
What is the CL, not CD?
Under root CD naught by K.
Okay.
Exactly. So that is 0.02 upon 0.019 square root, which you can just calculate and just tell me the value. 1.025, right? Okay, so that is the equation that we used. We know how to solve this. Okay. An airplane has a weight of 100 newtons at the beginning of the flight, and 20% of this weight is fuel. 20% of the initial weight is fuel. In a flight at speed 800 km per hour, please pay attention to the units. In the flight of speed 800 km per hour, the lift to drag ratio is 12 and TSFC, thrust specific fuel consumption of the engine, is 0.8. Obtain rough estimates of the range in kilometer and endurance in hour. So if the TSFC is given, what kind of an aircraft is this?
Propeller driven.
Jet.
Jet.
Thrust specific is jet engine.
Yes, thrust specific is jet engine. Okay. So what will the unit be? So your TSFC is given here as 0.8. What is the unit? It's per second. Okay. TSFC unit is per second. Okay. Now let's try to find out the rough estimates of range and endurance. When they say rough estimates, you go with average. Okay. So over the course of the flight, you have initial weight and you have final weight. So the average weight will be what? Average weight will be initial weight plus final weight by 2. So what is that? Initial weight is what? 180,000 plus what is the final weight? It's the initial weight minus the fuel's weight. So weight final is weight initial minus weight of fuel.
162,000 Newton.
0.2 into weight initial, so that is 162 Newton. Okay, so that is your final weight. So you take 16200.
This is the average weight. 162,000 Newton is the average. I told the final.
Oh, that is the average. Okay. Oh, what was the value for the final weight?
It was 144,000.
144. Yeah. So this was 162, right?
Yes.
So you got your average weight. Next, with this, what do? We find out the average thrust required. The average is nothing but what was the thrust required equation? Thrust required was?
W upon L by D.
Yes. What was it?
W upon L by D.
Correct. So I'll just write the average weight here. Weight average L by D. So your average weight is 162,000. L by D is given in the question as 12. So what is this average thrust?
13,500 Newton.
8,500 Newton. There's one more zero. Okay. Then what next? What do? We've got the thrust, average thrust required. Then what do? We also have this thrust specific fuel consumption. What do? We have to find out the range or the endurance, whichever you find convenient initially. What do? So if I multiply this thrust required into this thrust specific fuel consumption, what do I get? So fuel,
Rate of fuel consumption we will get. I think.
yes, fuel consumed per hour equal to this average thrust required into thrust specific fuel consumption. So I do that 13500 into 0.8 and I get 0.8.
450.
This is the value, right?
Yes.
Okay, that is the value. Per hour. Okay, this is per hour. So per hour, if this much fuel is consumed, you can see how much time it will take to consume the entire fuel. What was the weight of the complete fuel? This weight of fuel was what?
Ma'am,
Yes. Tell me.
it was
what-
1,44,000, ma'am.
Okay. So when I write F, I mean final. I'm sorry if it's confusing. So weight final is weight initial minus weight of the fuel. The weight of the fuel is 20% of the initial weight, which is what I'm writing here, which comes to, okay, right?
Yes, ma'am.
Yes, ma'am.
So it takes 1 hour to complete this much amount of fuel. So how much time will it take to complete 36,000? So that is your endurance. Rough estimate.
3.33 hours, I think.
Exactly. So it will be 3.33 hours. So that is your endurance in hours. Now, what about range? Now that we have the endurance, what about range? Range is distance is equal to speed into time, right? So
Yes,
they
ma'am.
give you
So
flight
endurance
speed.
into speed, yes.
Yes, 3.33 into 800, which gives you a rough estimate of the range, which comes to about 2.
2,664 kilometers.
Okay, so that is the rough estimate of range in kilometers. Is this clear? This was a slightly different question.
Ma'am, can you please explain the thrust part again? Like, how do you calculate it initially?
Okay, so the thrust required is this equation you understood, right?
Yes, ma'am. Yeah.
So I just plugged in the average weight into this and the L
Ma'am,
by D.
why do we have use the average weight?
Okay, so they've asked you for rough estimates of range that you cannot take. There is no, you can't find the exact range, right? We don't have all the properties here. We don't have
Yes,
the
ma'am.
efficiency. We don't have all the other terms. So that is why they've asked you for rough estimate. When they ask you for rough,
Excuse me, ma'am.
yes.
Ma'am, the unit of TSFC was per second or per hour here?
Okay, so yes. So let's just take it as per hour. It's not given in the question. We assume it to be per hour. That was a good catch.
Hmm.
Yes, yes. It should be per hour. Yes. Yeah. Okay, so is this clear? Somebody had asked the thrust. How did we calculate thrust? That's clear, right? I just plugged
Yes,
in the
ma'am.
average
Thrust is
weight.
clear. Yes.
So when the specific fuel consumption is given, you just multiply it with the thrust to see how much fuel is consumed per hour. So like somebody had said, it is the rate of fuel consumption. So that gives you this 10,800 newtons per hour. Now that you have the complete fuel, you see how long it will fly. And the range is just the multiplication of that, time and velocity. So this gives you the rough estimate of range and endurance. Okay, so with this, we come to the end of this session. Does anybody have any question? Does anybody have any questions from any of those week 3 weeks content or any of the questions that we discussed? Any of the questions that we discussed today also, if you have any questions, let me know.
No doubt, ma'am.
Okay. Okay. So then I
It's
think,
clear, madam.
okay, then I think we can conclude this session. I will, are you getting the recordings of the previous session?
Yes, madam.
Yes,
Yes,
ma'am.
it is available.
Yeah. Okay. So if you have any doubts, you can go through that, or you can put up the questions on the forum. Or otherwise, we will meet again next week on Tuesday. All the best for your assignment that is due tomorrow.
Thank you very much, ma'am. Thank you.
Thank you, ma'am.
So you can leave. We'll meet again next week.
Sure, bye.
Thank you, ma'am.